In this lesson, we'll once again look at linear differential equations. So let's just recall what those are. So let's begin with a function of x, which I'll label as a sub n of x, multiplied by the nth derivative of some function y with respect to x. And then in our differential equation, we can include lower order derivatives. So suppose we have another function of x, a sub n minus 1 of x, multiplied by the n minus 1 derivative of y with respect to x. And we can have other lower order derivatives. So let's continue that until finally we get to a term that has no derivative at all, so just a sub 0 of x multiplied by the function y. All of that added together is equal to another function, g of x, which is also just a function of x alone. And this is known as a linear differential equation of the nth order. As a very simple example, let's just write down the following. So we have to start with some function of x. So maybe that could be the cosine function, so cosine squared of x, and then multiplied by some derivative of y. Now just keep this really simple, let's make that the first derivative of y with respect to x. And to keep things really simple, let's not include any other derivatives of y, but just go directly to the a sub 0. And that's some other function of x, let's say tangent of x, and then times y. And on the other side, we have to have another function of x, so let's say that's secant squared of x. So there's just an example of a first order linear differential equation. Now there's a very important special case for these linear equations, and that's something known as the homogeneous equation. And the only difference for the homogeneous equation is that this g of x that's on the other side is always equal to 0. So we could have an a sub n of x times the nth derivative of y plus all the lower order derivatives down to our a sub 0 of x times y. So all of this stays the same. But when we add up these derivatives, they add up to 0. And that's the homogeneous case. Now the reason that that's important for us is that there's this following important property. Suppose that we have multiple solutions for the linear homogeneous equation. And let's just call these y1 of x, y2 of x, and we'll have a big list of these, so all the way up to y sub k of x. So if all of these are solutions, of the homogeneous equation, actually that should be a linear homogeneous equation, just as we have out here, then we can combine these functions together. So I'm going to use a constant c1 multiplied by the solution y1 of x plus another constant c2 multiplied by the solution y2 of x, and so on. We'll go all the way to the c sub k, another constant times y sub k of x. Then this is also a solution of the homogeneous linear differential equation. Now what we've done here is formed a new solution which is known as a linear combination of the existing solutions. So that'll be an important idea for us in this chapter. A linear combination is just a sum of constant multiples of the functions that are in this list. So the C1, C2, up to CK, they can be anything. The only restriction is that they are just numbers or constants. And that's called a linear combination of the y1, y2, up to yk. So here's another example that will just illustrate a linear combination of solutions. Suppose we have the following linear equation. Second derivative of y with respect to x plus y equals 0. So because there's a 0 on this side, this is a homogeneous linear differential equation. And later in the chapter, we'll be looking at methods of solving equations such as this. For right now, let's just suppose that we know what the solutions are. So one of the solutions is y1 equals sine of x. And we can see that that's a solution because if you differentiate sine of x twice, you'll get minus sine of x. So the first derivative becomes cosine, and then the second derivative is minus sine of x. So if we put minus sine of x here in place of the second derivative, add it to y itself, then yes, those two add up to 0, so sine of x is a solution. Another solution is very similar. That's y2 equals cosine of x. So these are both solutions for the linear homogeneous equation that we have here. And so by this result up here, if we take any linear combination of these two solutions, then we'll get yet another solution. So let's just add the two together. Sine of x plus cosine of x. And that would be a solution for the equation. Or let's multiply these by some constants. So let's take 2 sine of x and add that to 7 cosine of x. So another linear combination. And that also is a solution of the differential equation. So there are many other possible solutions that we can generate this way just by changing the values of the constants. And this is something known as the superposition principle. So when we combine solutions together, we get yet more solutions for the differential equation. Now the superposition principle works only in the case of a homogeneous differential equation. So you've got to have that 0 on the right side. So what we're going to be looking at is it possible to come up with a list of solutions that will generate all possible solutions for the differential equation? So that's called a fundamental set of solutions. And just very roughly speaking, a fundamental solution or fundamental set of solutions is a list of solutions that's as short as possible and yet will generate all possible solutions of the differential equation by taking various linear combinations. So that takes us into a little bit of linear algebra. So we're going to now look at some general theory behind linear combinations. So let's suppose that we have some functions. So an f1 of x, f2 of x, up to, let's say, fn of x. So that's a set of functions. Now they could be solutions to a differential equation, but right now we're looking at a little more general context where they're just a list of functions. Now this list of functions is said to be dependent or linearly dependent if there exists some constants, so C1, C2, up to Cn. So it lists exists some constants here, with the restriction that they're not every one equal to 0. So some of these could be 0, but just not the entire list 0. So not all 0, such that the linear combination C1 f1 of x plus C2 f2 of x, so do that same thing for all of these, plus Cn fn of x is equal to 0. So we're defining here a word called dependence. So this is what it means for functions to be linearly dependent. If there's a linear combination of the functions, that will produce 0. So let's see how this works in an example. Let's let our functions be f1 of x equals sine squared of x, f2 of x equals cosine squared of x, and f3 of x equals 1. And then we'll see that this list of functions is linearly dependent. Let's just take the sine squared of x, and then we'll take the cosine squared of x, add that in, and also involve the 1, and we'll subtract that. Okay, so what does that equal? So sine squared x plus cosine squared x is 1. Then we subtract 1, and that's equal to 0. And that's actually an equation that's demonstrating dependence among the functions. So sine squared of x is just f1 of x. Cosine squared is f2 of x. And then 1 is f3 of x. So we have that f1 of x plus f2 of x minus f3 of x is equal to 0. And so they all added up to 0 in this linear combination, and that demonstrates dependence among the functions. We have a dependent set. Now we can see what that tells us. We can just put the f3 on the other side of the equation, in a sense solve for f3. f3 of x is equal to f1 of x plus f2 of x. And that shows that f3 of x is really not necessary to be in our list of functions, because f3 of x is just simply a linear combination of the other two functions. So we could go back up to our list, we could strike out the f3 of x and not lose anything, because f3 of x is just would be produced by taking a certain linear combination of f1 of x and f2 of x.